Have you seen the shocking images flooding social media of snow falling in the heart of the Amazon rainforest, where temperatures haven't dropped below 70 degrees Fahrenheit in recorded history? Or wondered how one of Earth's most stable tropical ecosystems could suddenly experience weather patterns that seem to violate everything we know about climate physics? What if I told you that snow in the Amazon isn't just a freak weather event? It's a dramatic demonstration of Emmy Noether's conservation principles being pushed to their absolute limits, revealing how global energy systems can reach tipping points where familiar patterns collapse and impossible weather becomes inevitable. Today, I'm going to expose why the Amazon is experiencing unprecedented climate disruption that follows conservation laws, while simultaneously showing us how those same laws can create conditions that seem to break all the rules. The Amazon rainforest has functioned as Earth's climate stabilizer for millions of years, maintaining consistent tropical conditions through sophisticated feedback loops that regulate temperature, humidity, and precipitation across an area larger than the continental United States. This vast ecosystem operates like a massive thermal engine, continuously cycling water vapor, regulating atmospheric temperatures, and maintaining energy balance through processes that have remained remarkably stable throughout human civilization. The idea of snow falling in this tropical paradise should be as impossible as finding ice cubes in a functioning oven. Emmy Noether's insights about energy conservation help us understand both why the Amazon has been so climatically stable and why that stability can suddenly collapse when external forces disrupt these energy cycles beyond certain thresholds. The snow falling in the Amazon represents the climate system's response to energy disruptions that have pushed tropical weather patterns past their stability limits, forcing the system to reorganize in ways that produce previously impossible weather conditions. The physics of tropical weather systems reveal why snow in the Amazon represents such a dramatic violation of normal atmospheric energy distribution. Tropical climates exist because of consistent input from solar radiation combined with atmospheric circulation patterns that distribute warm, moist air throughout equatorial regions. The Amazon's position near the equator means it receives nearly constant, intense solar energy that should make snow formation thermodynamically impossible under normal conditions. Snow formation requires specific atmospheric conditions that violate the normal energy patterns of tropical climates. Temperatures must drop below freezing throughout a significant portion of the atmospheric column. Moisture must be present in sufficient quantities, and atmospheric dynamics must support the formation and preservation of ice crystals during their fall to Earth. For these conditions to exist in the Amazon, something fundamental must have changed in the global energy distribution systems that govern weather patterns. The meteorological analysis of Amazon snow events reveals the complex atmospheric dynamics that can temporarily override tropical climate patterns. High-altitude atmospheric rivers carrying Arctic air masses, disrupted jet stream patterns that allow polar air to penetrate tropical latitudes, and altered precipitation patterns that concentrate cooling effects in localized areas can all contribute to creating the impossible conditions needed for tropical snow. But the deeper question involves understanding how global energy systems became so disrupted that these extreme weather patterns became possible. Emmy Noether's conservation principles require that energy cannot be created or destroyed, it can only be redistributed. If the Amazon is experiencing unprecedented cooling, that thermal energy must be going somewhere else, following conservation laws that govern global climate systems. The global climate system operates as an integrated energy distribution network, where changes in one region create compensating changes elsewhere. The thermal energy that normally maintains tropical conditions in the Amazon might be getting redistributed to other parts of the planet, creating the energy imbalances that allow Arctic conditions to penetrate tropical latitudes. This represents conservation of energy on a planetary scale, where local climate disruptions reflect larger patterns of global energy redistribution. The role of ocean currents in global energy distribution provides another lens for understanding how Amazon snow might represent normal conservation processes operating under abnormal conditions. Ocean currents transport enormous amounts of thermal energy around the planet, and disruptions to these currents, caused by melting polar ice, changing salinity levels, or altered wind patterns, can redirect thermal energy in ways that dramatically change regional climate patterns. The Amazon's own contribution to global climate regulation helps explain how disruptions to rainforest ecosystems can create feedback loops that generate their own climate disruption. The Amazon produces much of its own rainfall through evapotranspiration, the process by which plants release water vapor that forms clouds and precipitation. Deforestation, drought, or other ecosystem disruptions can reduce this moisture production, altering local atmospheric dynamics in ways that make extreme weather events more likely. The mathematical modeling of climate systems reveals why small changes in energy input or distribution can create dramatically different weather outcomes. Climate systems exhibit what mathematicians call sensitive dependence on initial conditions. Small perturbations can amplify through feedback loops to create large changes in system behavior. Amazon snow might represent the amplified outcome of relatively small changes in global energy distribution patterns. The historical climate data shows that while Amazon snow is unprecedented in recorded history, Earth's climate systems have experienced dramatic shifts before, often in response to changes in global energy balance. Ice ages, volcanic winter events, and other climate disruptions demonstrate that Earth's climate system can reorganize rapidly when energy conservation equations are altered by external forces. The implications of Amazon snow extend beyond meteorological curiosity to fundamental questions about climate system stability and the limits of environmental resilience. If tropical ecosystems can experience Arctic weather conditions, it suggests that climate systems may be more fragile and more capable of dramatic reorganization than previously understood. This has profound implications for understanding climate change, ecosystem stability, and the potential for rapid environmental transitions. The conservation of biodiversity becomes a critical concern when climate systems undergo such dramatic reorganization. Amazon ecosystems evolved over millions of years to function within narrow temperature and humidity ranges. Snow and freezing temperatures represent energy conditions that tropical species have never encountered and cannot survive, potentially triggering ecosystem collapse that could affect global carbon cycles and climate regulation. The technological challenges of monitoring and predicting such extreme weather events also reveal the limits of current climate modeling capabilities. Weather prediction systems are calibrated based on historical patterns and normal ranges of atmospheric behavior. When climate systems begin producing impossible weather like Amazon snow, it exposes the gaps in our understanding of how conservation laws operate under extreme conditions. The economic implications of impossible weather events extend to agriculture, transportation, infrastructure, and global supply chains that depend on predictable climate patterns. Amazon snow represents not just a meteorological anomaly, but a disruption to the energy systems that support human civilization and economic activity throughout the tropical regions that contribute significantly to global food production and resource extraction. The psychological impact of seeing snow in the Amazon also demonstrates how impossible weather events can challenge human understanding and create anxiety about environmental stability. When familiar natural systems begin behaving in ways that seem to violate physical laws, it creates cognitive dissonance that reflects deeper concerns about environmental change and system stability. The next time you see images of snow falling in the Amazon rainforest, remember that you're witnessing Emmy Noether's conservation principles operating under extreme conditions that push climate systems beyond their normal stability ranges. The snow isn't violating physics, it's demonstrating how energy conservation can create seemingly impossible conditions when global energy distribution systems are disrupted beyond their normal operating parameters. The impossible weather represents conservation laws finding new equilibrium states that may seem to violate everything we expect from tropical climates. This climate disruption reveals the remarkable sensitivity of Earth's energy systems and the potential for rapid reorganization when conservation equations are altered by external forces. The Amazon snow serves as a dramatic reminder that climate systems, like all complex systems governed by conservation laws, can undergo sudden transitions that transform familiar patterns into previously impossible conditions. The implications extend far beyond meteorological interest to fundamental questions about environmental stability, ecosystem resilience, and the future of climate systems that have supported human civilization for thousands of years. Understanding the physics behind impossible weather helps us appreciate both the remarkable stability that has characterized Earth's climate and the potential for dramatic change when energy conservation systems are pushed beyond their stability limits.